Today I am explaining about the sequential logic circuits. A sequential logic circuit is a logic circuit where the output depends on the present value of the input signal as well as the previous input, while a combination circuit is a function of present input only. A sequential circuit is a combination of combinational circuit as well as the storage element. Gates and flip-flops are required for constructing a sequential logic circuit. Example for the sequential logic circuit: shift registers, counters, serial adder, RAM, etc. Memory element is required to store the past history of input variables in a sequential logic circuit. Flip-flops are used as a memory elements. In above figure as shown in PPT, there is the sequential circuit diagram. So here combination logic circuit. In combination logic circuit, it outputs depends on only present input, and the next block is digital storage. So here digital storage means there are different elements like flip-flops, shift registers, serial adder, counters. So here flip-flops are the digital storage elements, and in sequential circuit clock input is necessary here. The next explain about the RS latch using NAR gate. So before that, what is the difference in between flip-flop and latches? So latches are building blocks of a sequential circuit, and this can be built from logic gates. Flip-flops are also building blocks of sequential logic circuits, but this can be built from the latches. The second differentiation: latch continuously checks its inputs and changes its output correspondingly, and a flip-flop continuously checks its input and changes its output correspondingly only at times determined by clocking signals. That means in latches no clock signal required, but in flip-flop clock signal is required. The latch is sensitive to the duration of the pulse and can send or receive the data when the switch is on. Flip-flop is sensitive to a signal change. They can transfer data only at the signal instant, and data cannot be changed until next signal change. Flip-flops are used as a register. It is based on the enable function input. It works on the basis of clock pulses. It is a level triggered. It means that the output of the present state and input of the next state depends on the level, that is binary input 1 or 0, and in flip-flop it is an edge trigger. It means that the output and the next state input changes when there is a change in clock pulse, whether it may a positive or negative clock pulse. Now I am explain about the RS latch by using NOR gate. So here we can draw the RS latch by using the NOR gate. So here two NOR gates are cross coupled to each other and forming the RS latch. So this is cross coupled with the this one, and this input is cross coupled with the this, and this one is the R and this one is the S. R stand for reset, S stand for set, and here Q and Q bar are the output. So here it's a truth table. R S Q Q bar and states. Here R and S are the inputs, Q and Q bar are the output, and their state. So here 0 0 0 1 1 1 1 0 1 1 are the four different inputs, and based on this input you can verify the outputs Q and Q bar by using the NOR gate. So before that the NOR gate function is, do you know? So here 0 0, then output is 1 0 1, output is 0, and 1 0, output is 0, and 1 1, output is 0. So it notation is y is equal to a plus b bar. Based on that, that is the truth table of the NOR gate. So here before that I am applying 0 0. Before that I am applying input 0 0, I assigned input is 1. I am assigning output as logic 1 is 0. So now I am applying input R is 0. And here 1. 0 1 means 0 q bar. And the next I am applying 0 and this 0 0 0 is 1. So here I am assigning, before that applying the 0 0 input, q is 1, so q is 1 and q bar automatically 0, so the state is no change. And next applying 0 1. So here R is 0, R is 0 and already previous output is 1. So 0 1, 0 1 is 0, q bar is 0. And the next 1, this 1 and this 0, 1 0, 1 0, this 0, okay, and this 0 and 0, sorry, this 0 and this 0 is 1, so this is 1, so q is 1, q bar is 0, so this is set. And next 1 0, so here 1 and this is 0, 1 0 means 0 and 0 0 is 1, so this is the reset. Okay, so next 1 1, so here 1 and this 0, 1 0 0, 0 1 0, so that means indeterminate means forbidden state. So like that we can explain the RS latch by using the NAND gate here. So here now again explain here. Next, before going to analyze the RS latch, we recall that a logic 1 at any input of an OR gate forces its output to a logic 0 When r is equal to 0 and s is equal to 0, the output of the latch remains in its last state, that is q is equal to q0. This condition is called inactive state because nothing changes. When r is equal to 0 and s is equal to 1, the output of latch is set to logic 1, that is q is equal to 1. And when r is equal to 1 and s is equal to 0, the output of latch is reset to logic 0. And when r and s inputs both are high, then output of the latch is invalid. So this is called a forbidden state or invalid state. It is not used state or a prohibited state. The next, the truth table of the RS latch by using the NOR gate as shown in above PPT. So here whenever input is 0 0, then it state is no change. And when 0 1, the state is reset. And when 1 0, the state is set. And when both the inputs are 1 1, then state is forbidden, means invalid state, inactive state. Next, explain about the RS latch by using the NAND gate. So draw the circuit diagram of the NAND latch. So cross couple the two NAND gates, and then we form the S R RS latch. This is Q and this is Q bar. Then next to this one, then next to this one. And the symbol of the NAND is shown above, that is S and R are the inputs, and Q and Q bar are the outputs. And we can draw the truth table, that is S R Q Q bar and state or operation, that is 0 0 0 1 1 0 1 1. And here NAND gate truth table we know, that is 0 0 0 1 1 0 1 1. So its output is y is equal to a into b bar. So all 1 1 1 0, the output. Based on that we can operate the SR latch by using the NAND gate. So here before that I am assigning Q is 1 and here S and R 0 0. So I am applying R and previous Q is 1, so 0 1 0 1 is 1. And again here 1 and 0 0 is 1. So this is I am assigned output Q is 1, Q bar also 1, but as for analyze it is Q bar is 0, so then it is no change state. But here both are same, so it is a forbidden gap, or this state is not allowed any signals or any state. And then next applying next input 0 1. So here it is 1 and 0 0 1 is 1. And here 1 and 1 0. So it is Q is 1, Q bar is 0, so it is a set state. And next applying 1 0 1 0. So already previous is 0 here, so 1 0 1 0 is 1. It is Q bar is 0, so 0 1 is 1. And here 1 0 1 0 is 1. Okay, and 1 1 is 0, Q is 0, so this is a reset condition. Okay. And next when both are 1 1, here 1 1 0 0 1 1, so it is holding, means no change. So as for the given truth table, the operation is a high on the S input will set the RS latch, that is Q is equal to 1, Q bar is 0, and a high on the R input will reset it that is q is equal to 0 and q bar is equal to 1. If both r and s are high, the latch will remain in its previous state. When both R and S inputs are low, the output is invalid. The truth table of the RS latch by using NAND gate as shown in above PPT. So when both inputs 0 0, then operation is forbidden, means not allowed. So when 0 1, then it is a set condition, and when applying 1 0, then it is a reset condition, and when applying 1 1, then it is a hold condition. So this is the RS latch by using the NAND gate. Next, flip-flops. Flip-flops are the sequential logic circuit. So here a flip-flop or a latch in a circuit has a two state and can be here flip-flop is formed using logic gates which are in turns made of transistors. Flip-flop are basic building blocks in the memory of electronic devices. Each flip-flop can store 1 bit of data. These are also called as a sequential logic circuits. Next, two types of flip-flops. There are basically 4 different types of flip-flops, like SR flip-flop. S means set and R means reset here. R it is also known as a latch. JK flip-flop, D flip-flop. D means data or delay flip-flop, and T flip-flop. T means toggle, and the fifth one also is there, that is master slave JK flip-flop. Now I am explaining about the SR flip-flop. Computer use thousands of flip-flops to coordinate the overall action. A square wave signal called the clock is sent to each flip-flop. This signal prevents the flip-flops from changing state until the right time. So the logic diagram of the flip-flop as shown in above PPT. So here 4 different NAND gates are there, and we take S and R inputs at the first, third and fourth gate, and 1 and 2 NAND gates are cross coupled. And forming the clocked SR flip-flop here. So previously same we are done the SR latches by using NOR and NAR gates, NAND gates. Same as it is here, but here the flip-flops contains the clock signals. So shown the above PPT the two table of the clocked SR flip-flop. So here clock S R are the inputs, and S bar also input, and outputs Q and Q bar, and it state of the output is shown the PPT. Here applying a clock signal is 0. S and R inputs are 0 0, then S bar is 1, R bar is 1, and output Q is Qn and Q bar is Q bar. So the operation is no change in the previous state. And next, whenever applying next clock, that is 1, and S and R are the 0 0, then S bar and R bar is 1 1. Then same thing, output is Q and Q bar, no change in the previous state. And when applying 1 0, next clock is 1, clock signal is 1, and inputs S and R are the 0 1, then S bar is 1 and R bar is 0, then Q and Q bar are 0 1, so its state is reset. And when applying another clock signal, that is 1, so S and R are the 1 0, and S bar is 0 and R bar is 1, so output is 1 0, and state of the output is set. Whenever applying a clock signal is 1, then S and R are 1 1, and S bar and R bar is 0 0, Q and Q bar is 1 1, so it is invalid state or forbidden state. Here the positive level clocked SR flip-flop and its symbol are shown in above PPT. NAND gates 1 and 2 form a basic latch. NAND gate 3 and gate 3 and 4 are called steering gates or control gates because they are used to drive a NAND latch. And working principle, as long as the clock is at a low level, the NAND gates 3 and 4 are disabled irrespective of S and R inputs. Thus, the output remains in its previous state, that is Q is equal to Q naught. The case 2, when the clock is at high level, means clock signal is 1, the inputs control the outputs as follows. If S is equal to 0 and R is equal to 0, then the output of NAND gates 3 and 4 at high. Due to this, the latch will not change its output state, means previous state. Next, if S is equal to 0 and R is equal to 1, then S bar is equal to 1 and R bar is equal to 0. With these inputs, the latch is reset to 0 irrespective of its previous state. If S is equal to 1 and R is equal to 0, then S bar is equal to 0 and R bar is equal to 1. With these inputs, the latch is set to 1 irrespective of its previous state. This case S is equal to 1 and R is equal to 1 is not used as its ambiguous or invalid state. So in truth table above PPT, clock signal is 0, SR no change, means Q is Q naught, no change. The clock is high, then SR 0 0, then state is no change, and 0 1, Q is 0, that means reset, and 1 0 means Q naught is 1, and output operation is set, and it is 1 1, it is forbidden, that means not perfect output here. Computers uses thousands of flip-flops to coordinate the overall action. A square wave signal called the clock is set to each flip-flop. This signal prevents the flip-flops from changing states until the right time. Right time. Positive level clocked SR flip-flop and its symbol are shown in above PPT. NAND gates 1 and 2 form a basic latch. NAND gate 3 and 4 are called steering gates or control gates because they are used to drive a NAND latch. The operation case 1. As long as the clock is at a low level, the NAND gates 3 and 4 are disabled irrespective of S and R inputs. Thus, the output remains in its previous state. Case 2. When the clock is at a high level, the input controls the output as follows. If S is equal to 0 and R is equal to 0, then the output of NAND gates 3 and 4 at a high. Due to this, the latch will not change its output state, that is Q is equal to Q naught. If S is equal to 0 and R is equal to 1, then S bar is equal to 1 and R bar is equal to 0. With these inputs, the latch is reset to 0 irrespective of its previous state. If S is equal to 1 and R is equal to 0, then S bar is equal to 0 and R bar is equal to 1. With these inputs, the latch is set to 1 irrespective of its previous state. The case S is equal to 1 and R is equal to 1 is not used as its ambiguous or invalid state. So, truth table of the clocked SR flip-flop as shown in above PPT. Clock is 0, then SR is invalid, XX. So, state is no change. When the clock is high, that means 1, applying input 0, 0, then output is previous state. When applying clock is high, 0, 1, then operation is reset. And when the clock is high, applying SR is 1, 0, then output is 1, 0, Q and Q bar, and it is set. And when applying clock is 1 and S and R is 1, 1, then S bar R bar is equal to 0, 0, and Q and Q bar are 1, 1, and it is invalid, forbidden, or invalid state, means it is not a defined state. So these are about the RS latches by using NAND and NOR gates and basics of the sequential logic circuits. The difference in between latches and flip-flops, and different types of flip-flops. Among that 4 types, today we discuss about the clocked SR flip flop. Thank you.